Okay, so now we are ready to talk about very large stars and how they're going to die. So these are going to be stars that are greater than 30 times the mass of our sun. So our sun is never going to turn into a black hole. For that matter, our sun is never going to turn into a neutron star. So we're just going to be talking now about the very large stars and what they're going to do. Notice that they go through all of these stages that the large stars did. So that they're first going to be converting hydrogen to helium, then they're going to convert the helium into carbon, then the carbon into neon. They're going to go all the way up to iron. They're going to manufacture iron. They're going to collapse. They're going to go supernova. But this time, not even the nuclear degeneracy pressure is going to be strong enough to hold gravity at bay. So that there's absolutely positively no force in the known universe that can keep gravity from crushing this thing down until it no longer ceases to exist in our universe. So physically speaking, talking about the diameter of this object, it's a mathematical point. So it has no dimensions to it. It has zero radius, zero diameter. But it still has all of its mass. So you're saying to yourself, how's that possible? Just go with it, okay? So the idea of the black hole was something that Stephen Hawking, the guy in the wheelchair, worked on. And so he came up with a lot of these ideas on how black holes ought to operate. Now, a black hole does have a size to it. Okay, so if I put a dot to represent where the singularity is, so this is where the black hole really is. And it has no physical size to it, but all the mass is concentrated at this point. So that's going to be called the singularity. So surrounding this thing is going to be the event horizon. So the event horizon is how close light can get to the black hole without being sucked in. So do you remember when we talked about the orbits of rocket ships and the orbits of planets, and we said that you had a circular speed and then you had escape speed. So if a rocket had escape speed, it could escape the gravity of an object. And what was the ultimate escape speed? The speed of light. So that if light is right here, then it would have enough energy in order to be able to escape the gravity of this black hole. But if the light was in here, it would try to escape, but it would be pulled back into the black hole. So that means if this light doesn't escape, then you don't see the light. So that means that this is going to be black. And so that's why we call them black holes. So this represents the edge of a black hole. But physically, the black hole's in the center here. It's in what's called the singularity of the black hole. Okay, so what are some properties of black holes? Well, they do have what's known as an accretion disk. And so the accretion disk is going to be out here, and it's going to be material that is circling around and around, and it's going to be waiting its turn to be sucked into the black hole. And the faster it goes around and around, the more radiation that it's going to emit. It's accelerating. And we said that accelerating electrical charges produce the electromagnetic spectrum. So as this material is going around and around, waiting to go into the black hole, it's accelerating and it's going to be producing light. And so in this picture here, down there at the bottom, you have the black hole's in the middle, the black part, and then surrounding it is this ring of material. It's a disk of material, And then that disk, that's going to be called the accretion disk. And the reason why you can see it is because that material, as it's going around and around, is accelerating and it's producing electromagnetic radiation. And it's, in particular, it's going to be producing X-rays. So because it's going around and around so fast, it's producing the highest, well, not the highest, but it's producing very high energy radiation X-rays. So if you are looking for black holes, what you ought to be looking for is X-rays. So here is, again, a picture showing the magnetic field of the black hole. So notice that even a black hole is going to have a magnetic field. The black hole can be spinning, just like the neutron star can be spinning. But it's also going to have this accretion disk out here where material is waiting its turn to go into the black hole. Now above it, it's showing what is the black hole doing to space and time. So when we talked about gravity, we said the correct way of thinking about gravity is the bending of space and time. Space-time is 3 dimensions of space and then 1 dimension of time. You put the 4 things together and you get 4-dimensional space-time. So we can represent space, 1 dimension of space, and then 1 dimension of time, and then that would be space-time. Now, in fact, though, you can't represent 4 dimensions in 3 dimensions. So this is representing 2 of the dimensions, so like the x dimension and the time dimension. So that's flat space-time. That's what space-time would look like if there's no stars present. Now let's say that there is a star. So then what happens is the mass of a star bends space and time. Just like if you take a bowling ball and you throw it onto your bed is going to make a dimple. So that's the bending of the covers caused by the mass of the bowling ball. This is the bending of space and time caused by the mass of a star. Now when a star turns into a black hole, it's going to rupture space and time. So then instead of doing that, it's going to do this. And it's going to come to a point, and then that point down there, that's where the singularity is going to be. So you have tremendous distortion of space and time as you get closer and closer to that singularity. So one of the things that would change, let's say you're an astronaut and you're falling into the black hole, well, your shoulders would get closer and closer together. So your shoulders would be this far apart, then this far apart, then this far apart. So you'd be squeezed to death as you fall into the black hole. Another thing would be your feet. Let's say you fall feet first into the black hole. Your feet would be closer to the black hole than what your head would be. So therefore your feet would feel more gravity. So as you fall into the black hole, you would be stretched at the same time. So your shoulders would be crushed, but your feet and your head would be pulled apart as you fall in. Then another thing is what would happen to time itself. So that from the point of view of somebody on Earth watching you fall into a black hole, they would see time for them would be normal. But looking at the astronaut, they would see the astronaut going slower and slower and slower until they were at the event horizon, and then they would stop moving. They would be frozen in time for all time. If, on the other hand, you were the astronaut and you were falling into the black hole, you would notice your wristwatch is normal, but looking outwards, you would see time sped up, and you would see the end of the universe. All the stars use up their fuel and wink out of existence before you fell into the black hole. All right, so there are other theories as to what would it be like to fall into a black hole. So if you want to do this, there is a YouTube video there that you can watch, and they explain some of the things that might happen to you as you fall into a black hole. I highly recommend that you watch it. So it's a very good video. All right, so we've talked about this slide here, reasons why stars do not collapse. Here is our summary. Okay, so we're starting with the nebula over on this side. It's going to collapse. Okay, if the nebula doesn't ignite, then that is going to be the brown dwarf, which turns into the black dwarf. Now, let's say that it does ignite, but it only can convert hydrogen into helium. That's going to be the red dwarf turning into the black dwarf. Okay, now let's say it ignites and it can make other elements. Okay, then it's going to turn into a red giant, and then a planetary nebula, and then what's left over is going to be the white dwarf, which eventually turns into the black dwarf. Okay, then up at the top, it could manufacture iron, and it could explode. So that's the supernova. But then, depending on the size, it either turns into the neutron star or it turns into the black hole. So that's all of those different processes summarized on that chart there. Then there is another simulation that you can look at if you're interested. You're not going to be tested on this, but it's called Star in a Box. And what you can do is you can change the slider on this thing, and you can change the initial mass of the object and then see what happens to it. And you can see how it might turn into a brown dwarf, and then black dwarf, red dwarf, black dwarf, and so forth. So you can change the initial mass of the object, and you can see how it would change on the HR diagram on this little thing right here. Okay, we're going to take one last break, and when we come back, we're going to do our lesson quiz.